All right, so welcome back. So we've derived now our formula for the derivative, the slope of the tangent line at a point where we're at the point of r theta in polar coordinates. Again, remember the idea is that the slope of the tangent line, the derivative will be f prime theta sine theta plus f theta cosine theta over f prime theta cosine theta minus f theta sine theta. Okay, so let's see an example here. And this first example is going to be pretty straightforward. Here we just have a function that's a constant. So we want to find dy dx, the formula for the derivative. So remember the idea here is that x equals r cosine theta and y equals r sine theta. In this case, that would be x equals 2 cosine theta and y equals 2 sine theta. So we could use the derivative formula up here, or just realize that in this derivative formula, the first terms are both going to be 0 because r is a constant. And then you can use the formula just for the other two terms. Or we can just, again, use the idea, which it's just going to be the derivative of y with respect to theta over the derivative of x with respect to theta. Okay, so dy dx would be the derivative of y with respect to theta. So that would be 2 times the cosine of theta over the derivative of x, which would be 2 times the negative cosine, 2 times the negative sine, which would be negative 2 sine theta. The 2's cancel out, and we actually get negative cotangent of theta. It turns out the derivative here, the slope of the tangent line, is actually the negative cotangent of the angle. Negative cotangent of the angle. And then we can ask about finding it for a specific place. So we might say find the slope of the tangent at theta equals pi over 4. Theta equals pi over 4. So we take our dy dx function, and we're going to evaluate it when theta equals pi over 4. In other words, plug pi over 4 into our cotangent function. Of course, cotangent of pi over 4 is the reciprocal of tangent of pi over 4. Tangent of pi over 4 is 1, so cotangent is 1. You have the 1 in front. So the slope of the tangent line here would actually be negative 1. Okay. Would be negative 1. Okay. All right, and we can show this really simply that this idea does work if we were to look at the graph of the circle, r equals 2. All right, it's just a circle centered at the origin. So let me just draw a circle in here, centered at the origin. Right, and at pi over 4, that would be, in other words, at 45 degrees, at an angle of 45 degrees, coming out here, we would have our tangent line, and it would be this tangent line right here. It looks something like this. Now, I can actually explain to you and demonstrate that this tangent line on the circle here has to actually have a slope of 1 without even finding any points. And we can do that in the following way. Remember that the tangent is 1, right? The tangent is 1. So if I complete the circle, that means the x and y values are equal. That means this line here going up actually has a slope of 1. Change in y over change in x. Okay, so I know that this line here has to have a slope of 1. Okay. Then I know that the tangent and the radial line here are actually perpendicular. That's a result from geometry. So this line has to be perpendicular to the line of slope 1. Well, from that, we know that slopes of perpendicular lines, the one is the opposite of the reciprocal of the other. So since this line has a slope of 1, this line here has to have a slope of minus 1. Right? It's the opposite, so minus of the reciprocal of 1, which is 1. And so we can actually get that slope there from geometry, a little bit of knowledge about geometry. And that just confirms that our result works. But not only does it work at an angle of pi over 4, it'll work at any other angle as well.